Okay, so one of the goals of developing Astra, or one of my goals in developing Astra, was to use a static type system. And remember, static types is like the way that we do things in Java, and dynamic types is the way that we use define variables in languages like Python or JavaScript, where the variables can change the type. In Java, the variable has a fixed type and it can't change from that type at all during the execution. It always must have values that are the relevant type, and if you try to store a value of the incorrect type in a typed variable, then you get a compile time error. And part of the reason for this is because I noticed that, as I say, a lot of my experiences of people building and writing code with dynamically typed agents was that dynamically typed languages was that they would often forget what type of data they were using, and they would start to use the wrong type of data, and then they'd have these sort of hidden logic errors occurring where you're trying to check for an integer but you put a string or things like that, and all these sort of problems were very difficult. These logic errors are very difficult to solve because they all were only detectable at runtime, and by using static types we're able to capture some of those errors at design time, at compile time. But my use of static types also is inspired by the way I wanted to integrate ASTRA with the underlying Java language. So ASTRA is essentially an interpreter built in Java, and it sits on top of Java. What I wanted to be able to do is to find a very clear way that you could sort of essentially write code in Java that could be executed from the ASTRA level. And think in terms of, for example, primitive actions. All the primitive actions you want to be able to perform. If there was a clear mapping from a primitive, from the ASTRA level code, where you declare what action you want to perform, to the underlying implementation of that action in Java, then it would hopefully make things easier and cleaner in the long run. So, not only is ASTRA a statically typed language, but the type system I've used is based largely on Java. There are some differences to reflect the nature of a logical language over a procedural language or object-oriented languages like Java. But essentially ASTRA has all the primitive types that are most of the primitive types that are supported by ASTRA. So Java ASTRA contains most of the primitive types that are supported by Java. So we definitely have support for short, sints, longs, floats, doubles, booleans, and chars. There are probably other types that I don't provide direct support for, and that's just potentially just, that was the ones that I felt I needed. I suppose if you need more, you can always submit an issue to the issue tracker requesting an enhancement to add that type in. It wasn't that difficult to add more types in. I think I got all the types, but I'm not 100% sure. I didn't do an exhaustive check. But in addition to having these primitive types that are the same as ASTRA, what we did do is we introduced a primitive type called string, which is the equivalent of Java lang strings. So strings in ASTRA are primitives, but in Java they're an object. Okay, so strings were treated a little bit differently to Java because strings are used extensively within most agent-oriented programming languages, and I needed it to be a primitive type. Also, because languages have this concept of a logical list that we talked about last week and the week before, I introduced a list type to represent logical lists, and I also introduced a func type for functional terms. Now, the functional type stuff we're not going to really talk about too much this week. We'll maybe introduce it later on in the module. We may not. The other type of thing that I supported within ASTRA is object references, and this was quite different to the way that most object-oriented languages work. I can pass a reference from Java to ASTRA, so an object reference, and I can pass that in, store that in my beliefs. I can manipulate it in various ways, and then I can drop it back down into Java code again from ASTRA to use it. So that gives me a really sort of powerful mechanism for basically doing things like builder type patterns, where you basically have an object that you have a set of actions that can modify the object to construct the object you want to use in a more complex scenario. So that's probably a little bit over the top what I just said there, but essentially what I'm trying to say here is that in ASTRA I basically said, well, look, I'm going to copy what Java did, but with a few exceptions. So I copied the primitive types to Java. I added a string type because I felt that was necessary for ASTRA rather than relying on the string class. I introduced a list type for dealing with lists. and there is a corresponding Java implementation of that list type, which I'll come back to later. I introduced a functional type for functional terms, and I did explicitly include support for object references. And whenever you want to deal with an object reference, you just use the class name, just as in the same way that you would do it in Java. And I may or may not show you that later on, depending on whether we need to show it or not. Okay. As I said before, the purpose of this was to simplify the integration, because essentially the two reasons. One was to capture, stop so many runtime errors by trying to catch more errors at compile time, and the second was that I wanted to make sure there was a clear correspondence between an action you're trying to invoke and the implementation of that action in Java. And the way I mapped those things was I mapped actions to methods in Java. So the signature of the method had to correspond to the signature of the action. So whatever action I declared, the action name had to become the method name, and the number of parameters had to match, and the types of the parameters had to match. Okay. Anyway, so this is something we'll look at next, or in a few videos, when we sort of focus in around the idea of modules, which is this way that I support the implementation of custom actions and so on. But what I want to do for the remainder of this part is just to come back and look at the idea of types in a bit more detail and have a very quick scan through. I mean, types are a fundamental part of the ASTRA language, and I'm going to keep referring to types and talking about types all the way through the slides, the various videos that I do. So it's something that's we're going to come back to again, but just to kind of get us started, I want to go back and look at that tic-tac-toe game we created before. So if you remember, in the original tic-tac-toe game, this was the set of predicates that I defined. This is back in the data modeling first lab. Well, here you've got to map that set of predicates to a tic-tac-toe agent. We need to create a tic-tac-toe ontology. Then, but the name doesn't really matter. It's just I'm using a standard name because I'm lazy. I just replaced tower with tic-tac-toe. But the types are formula, token of type string, so that's the first one. Played, which takes an integer count and a string, because x was a location, which was an integer number, and y was a string, which was the token. We could have used a character for y in this case if we wanted. Free is an integer because it's a position. Winner is a string because it's the name of it's the player, the x or the o. Loser is an x or an o, so it's a string. Drawn is an x or an o because it's a string. Drawn is x is a string here because drawn is an x or an o again. There were also two additional sort of predicates we introduced during the programming, the mental programming. We introduced a line predicate, which was essentially a winning line within tic-tac-toe, and we introduced a move predicate to capture the idea of this is the move that we're playing. Okay, so if you remember, the program that we implemented for this, and this is the program I gave you in one of the lectures, is we had this sort of initial state, a set of inferences, a set of initial beliefs about the winning lines, and this was the behavior, this was the rules or the plans that we used to implement the player's game playing behavior. Well, if we take this example program, we can map this to ASTRA, and so here we have a tic-tac-toe agent, we have a type statement that we had in the 2 slides before, then we have an inference that L is free, can be inferred if there is no belief played some token at position L. We've got the one for the winner, so T is the winner. If there's no line, and again you see that the first time that I use a variable, I declare it. So I call this an inline declaration of a variable. So here I declare L as an integer. It's the first time it occurs, and then I say here, so this L must be the same L as this. So this must be an integer L, and we say if there is some string T such that played T comma L is true, then this is not true. Yeah, and you can see again here, I declare my T on the left. It says typically any time, all of these inferences, the left hand side will always contain at least one inline variable declaration, and then the right hand side will contain 0 or more inline variable declarations, depending on the inference you're making. Here we've got the initial set of winning lines. And again, you can see here you've got a winner is if you've got a line, and the token that you're trying to check if it's 1 is played at each of the locations in the line. So in the game, we had two. So if we go back again and have a look, the game we had our turn rule and our move rules. So here we have our turn rule and our move rules. These are very similar. You can see this sort of mapping between them. Of course, this move action here that I talked about in in the lecture, we don't know how to do this yet. Okay, we can't do that because we haven't actually implemented a move action before. We don't even know how to implement actions at the moment, and certainly we'll have to come back to look at that again in the future. Maybe we'll look at it when we'll maybe build a simple tic-tac-toe module so that I can show you how this will all work, and we can build that into a game. Okay, so you can't do this, but the rest of it is all valid. I've made one little mistake, which I'm just going to rectify. Sorry. So that shouldn't be. So I don't have a question mark in Astra. It should be query like that. Okay. So again, apologies, I forgot to change that. So I will. The uploaded slide will look correctly. So when we do a query, if we want to query the state, we use the keyword query instead of a question mark. So having a look at lists as a second example, this was another example I did in the last lecture where I talked about the tower and building a tower. Well, this is the equivalent Astra code to this, Astra implementation of this. So we have our initial goal, tower CBA. Notice the constants become strings. They have to be types of values, so they become string values. We see here the rule that we have a tower with a list T, well this I've used T instead of L. Let me just again fix this up, make it exactly the same. So there's no confusion. So we have a goal to build a tower with the list L, and we achieve that goal to build a tower by calling the build sub goal, which takes in our list and a table. Notice I've made the question. Notice here I've fixed all the quotations so that you can copy and paste this in. We have again a rule here that says if you try to build an empty list onto some base, already achieved it. That's the equivalent rule in Astra is this one here. And then we have the rule that says if you want to build, if you've got a list that's not empty, then split it on the head and the tail. And you've got a base, then do the on HB and build HT, TH. So here we say if we've got the splitter, and again you see you have to know the type of the value in the list, although the type is not known in advance. And lists can be heterogeneous type, so you can have integers and strings, but we're assuming it's a string. So saying split the list into a head and a tail. You've got your base string B, put H on B, and build, recursively call the build sub goal with the tail and H. I mean, we'll keep calling these and keep posting this and keep building this, and we'll build the tower incrementally. Okay, so that's my sort of introduction to types. I realise that I'm not going to exhaust the list. I assume that you understand what a type is from your programming experience, okay? And I assume that kind of what I'm talking about gives some illustration as to how types are used. I've tried to focus on the list type a little bit because the list type is different to Java. But you can see here that the type system is a little. Hopefully, this example here gives you enough examples around how types are used and declared. Types are declared on the left-hand side of inference rules. And then can be used on the right hand side. You can also introduce other variables in the right hand side, but they are not passed back to the left hand side. So here, the value, whatever value, so this is not going to be so in here, whatever L1, L2, and L3 are, we lose the values, the variable bindings for L1, L2, and L3 when we find that T is a winner. So all we get back is the value for T. Okay. So again, we'll look at that another time. Maybe again, we'll come back to this as we do some more programs. What remains is to do this idea of moves. That's another big problem we have, and I suppose I'll look at that in the next segment.